Now we're looking at the fundamental theorem of calculus and how we can use the antiderivative of our function to quickly and easily evaluate the definite integral rather than going through that big long definition of the definite integral process with the limit and so forth. But there's some functions that we don't have a nice immediate way to show what the antiderivative is. And one of those functions is this absolute value. Now what we're going to have to do here, well, first of all, to get an idea of what this looks like, let's go ahead and graph this function. Does anybody remember what the graph of an absolute value looks like? What shape is it? Okay, it's a V shape. So as we look at that, well, in this case, where is, I guess we could call it the vertex. Where's the point of the V going to end up? Well, if x is 3, that'll make the inside 0. And then -4 with this last part. So 3, -4. And then, well, to graph it a little bit more accurately, try to draw as straight as I can here. And especially where the integral, we're going from 0 to 6. Let's see, so if x is 0, we'll be at -1. If x is 6, yeah, also at -1. So graphing this, we get this V shape. Well, if it doesn't fit, just draw a bigger dot, right? We get this V-shaped graph, and this can kind of help us see what we're going to have to do. We're really going to have to split this up into two parts. Now, by definition, let's just look at the absolute value of x. We have to define this as a piecewise defined function because we get two different results in terms of x depending on what the x value is. If x is a positive number, the absolute value of x then is, well, that same number. Absolute value of 3 is 3. So that's going to be one piece of it. And this is true for any positive numbers, but we could also include equal to 0. Absolute value of 0 is 0. But how do we have to write the absolute value of a negative number? If x is -3, absolute value of -3 is +3. So we start with x equal -3, but we end up with +3. +3 is the opposite of -3. +2 is the opposite of -2. So if x is negative, the absolute value of x is the opposite of x. Now, to be able to write this function here, well, absolute value of x minus 3, that's not going to be split in terms of 0, but where is it going to split up? At x equals x equals 3. Okay. Graphically, we can see at this point right here, it switches from one line to a different line. Okay. And as we look at that, I guess we can say greater than or equal to 3. Again, the nice, easy one, the inside remains the same as the result of the absolute value if the inside is greater than or equal to 0. In this case, if x is greater than or equal to 3, this will be just x minus 3. And then we have the x minus 7. So for x being greater than or equal to 3, the function value could be simplified to just x minus 7. What about the other part? What about for x being less than 3? What do we have to do here? Well, go back to our definition. For x being less than 3, the inside will end up being negative. So this is saying we take the opposite of the inside. Now we got to be careful because it's a binomial on the inside, but the opposite of the quantity x minus 3, and then minus 4, and that takes a little bit more work to simplify, but we'd have negative x plus 3 minus 4, or negative x minus 1 as that part of the graph. Now think about this looking at this line right here. Okay. We're saying that that part of this absolute value will be the line negative x minus 1. Does that make sense? Okay. Slope-intercept form, the y-intercept is negative 1, 0, negative 1, and then we have a slope of negative 1, so down 1 and over 1. But that's only the case up to 3. Then it switches to y equals x minus 7 for this part. So this function right here changes into a piecewise defined function, and we're going to have to split it into two parts when we look at it from 0 to 6. We're going to have to split it at 3 to be able to do the definite integral on it. So splitting this up, we have a integral property, a definite integral property that says we can go from 0 to some point, okay, and from 0 to 3 we found our function value would be negative x minus 1, and then we can add the second part of it, as long as we're starting again at 3. We can break 0 to 6 up 0 to 3 and then 3 to 6. And our second piece was what function? That was the x minus 7. So this absolute value function needs to be separated into its two parts so we can use our fundamental theorem now. So evaluating from 0 to 3, negative x minus 1 with respect to x, antiderivative of this piece, okay, and evaluating that from 0 to 3, we'll finish out that part of it after we do the antiderivative here. Antiderivative of x minus 7 is, Well, x squared over 2 minus 7x, and that goes from 3 to 6. So the fundamental theorem says we take our antiderivative and we plug in the top number then subtract the bottom number. Hopefully we won't need a calculator for that one, but I like 0. And we do the same thing here for our second part. Plug in the top, subtract the bottom, and like normal, I run out of room. And now, just calculate all this. Now, be very careful. This right here is the opposite of 3 squared. We're not squaring negative 3. We're squaring 3 and then taking the opposite of it. I'll go ahead and calculate that one for you. I know that would be a little tough on you, but end up with 0 there. Then plus 36 divided by 2, so 18 there. Minus 42, and then now this piece we are subtracting, and we're going to have more than just 0 there. So that's, if a little mistake occurs, it's usually that piece right there. We'll have minus 9/2 for this part, but then we subtract a negative 21, so we'd have plus 21 on that one. And now add all these together, and we end up with what? So we get a value for this definite integral of negative 15. Okay. Now, as we were developing the definite integral, we were illustrating it in terms of area under a curve, and we always ended up with a positive value. Area represents a positive value. What would a negative area mean? Well, don't try to think too hard on that. You might blow a few brain cells, but negative area doesn't exist, but we can end up with a negative value for a definite integral. Now let's see, there is a relationship here between the area and this value. Let's see what that is. Here is our graph from 0 to 6 of our absolute value, and let's find the area under the x-axis and above the curve. Well, to do that, a couple different ways. One, probably the most straightforward, let's split this up into 2 parts. There's a rectangle, and then here's a triangle. Area of that rectangle, length times width, we get 6 for the area of that rectangle. What about the triangle? 1/2 times the base, which again is 6, times the height. What's the height of that triangle? Now going from -1 down to -4 is 3. So 1/2 of 6 is 3, times 3 is 9. Total area represented by this figure is 15. The definite integral we ended up with was -15. Okay. So the definite integral if any area lies below the x-axis when we're calculating a definite integral, it's going to correspond to a negative value of the area calculating the definite integral for that part. If the area is above the x-axis, then the definite integral will correlate to a positive value of that area. Now, let's take this one step farther, okay, and we'll look at a function defined by a graph. Okay. Here's a graph where part of it's below the x-axis, part of it's above. We're going to evaluate the definite integral of this function, whatever it is. We don't need the equation of the function since we have the graph. Well, since it's an easy linear piecewise defined function, we can just look at the area of the region above and below the x-axis. Now, we will have to split this into parts. We start from 1, so we've got to think about from here over to 4. Okay. And, well, we kind of have to separate this. If we go from 1 over to this point, and let's see, that is going to be 2.5. Okay, the way the line goes, the slope of the line is -2. So if we go down 1, we're going to be over here at 2.5. We have to pick that point because that's where the graph crosses the x-axis. So from 1 to 2.5, the area above the x-axis will represent the value of that definite integral. And what could we say is the value of that, or is the area of that? Hard part here, or not really hard, but the little bit more work to it. Area of that triangle, 1/2 the base, which is another 1/2, times the height, which is just 1. Area of that triangle would be 1/4. So from 1, area of this square is 1 plus the area of that triangle. That is the integral from 1 to 2.5. Now, the next part here, let's see. Oh, I didn't pick a really nice graph. What's our x value at this point? The slope of this line is actually 3. We go up 3 and over 1. So if we only go up 1, we go over 1/3. So this x value will be 3 1/3. Okay. Well, from 2.5 to 3 1/3, the area represented by that graph, that's going to be under the x-axis. So that definite integral value is actually going to be negative. And it's going to be the negative of this area. Well, I can kind of maybe look at it as, let's see, from 2.5 to 3 1/3. The base of that, well, the height's going to be 1. The base will be 3 1/3 minus 2 1/2, which is, so we get 5/6 for the base of this one. So negative 1/2 base times height. Okay. And that gets us to 3 1/3. And then finally, from 3 1/3 to 4, well, we have another triangle, and the area is above the x-axis, so the definite integral will be a positive. 1/2 base of this one is 2/3, and height of 2. So we get 2/3 for that one. So as we add all this up, well, 5/4 minus 5/12 plus 2/3. And of course, as a fraction, 12 would be your least common denominator. So our fraction would be 18/12, or what, 1 1/2. So the definite integral evaluated from 1 to 4 based on area and where that area is. Above the x-axis, definite integral would be positive. Below the x-axis, definite integral would be negative. We get a value of 1.5 for that integral. Questions?